guys get this? Everyone else get this number? Okay. So now, how do we calculate the half-life? So at T equals 37 degrees, we said that K is equal to 0.092. So now we can plug in our equation. T1 half is equal to 0.69 divided by 0.092. And if we do this calculation, what do we get for a half-life? We get 7.5. 7.5. I think check your calculation for K, because this should be a bigger number. Because really, see, what this is telling us is that at 60 degrees, it takes 2 minutes for half of the DNA to uncoil. At body temperature, it takes only 7.5 minutes, just a little bit longer, for half the amount of DNA to uncoil. And that means that we better be regenerating DNA pretty quickly, because we don't want our DNA to uncoil. So check our number here. Check our number for this, for K2. Okay, so note again, for EA, did you plug in 430,000?
Yeah.
So we have 430,000 here divided by 8.31, and you have 333 minus 310 divided by okay, so maybe okay, so we have the natural log of 0.345. Okay, so what is the right side of the equation equal?
11.23.
So this is 11.53. That's the natural log of 0.345 divided by K2. So then the next step is take
Both sides to the E.
yeah, so we have then from here, we have 0.345 divided by K2 is equal to E to the 11.53 power. And that's even a big number, E to the 11.53 power. 101,000, so we have, that's 101,742.
Yeah.
I think so, Mark. And then we can solve for K2. So K2 is equal to 0.345 divided by 101,722. And we should get a smaller number than 0.092. 3.4 times 10 to the minus 6. So that's our K2. So let's go down, calculate our half-life. So this is 3.4 times 10 to the minus 6. So we have 0.69 divided by that number. And for our half-life at 37 degrees body temperature, 203,000 minutes. And how many hours is that? Or days? 140 days. Yeah, because this makes sense. Because note that at body temperature, we don't want the DNA to uncoil. It takes a long time for half that DNA to uncoil. Okay, so we'll do questions C, D, and E on Thursday in lecture. I just want to spend the last 5 minutes starting the calculation for that iodine clock reaction. So let's go back to that slide. You guys done with this slide? Okay, so let's go back to okay, so this is the reaction that you'll be doing in lab today. So solution A is this IO3 minus solution, and the concentration is 0.02 molar. HSO3 minus, this is solution B, the concentration is 0.002 molar. Now what we want to do is, you're going to use method 1, so you're going to do several experiments using different concentrations of IO3 minus and HSO3 minus. You're going to measure the time it takes for these colorless solutions to turn blue. And you're also going to measure, so that would be delta time here. You also want to measure the change in IO3 minus concentration. Okay, so to figure out the order of the reaction with respect to IO3 minus and HSO3 minus, we need to know these two concentrations. We also need to know the change in time, that is the amount of time it takes for the solution to turn blue. We also need to know this change in concentration here. Okay, so we'll get started in the last 3 minutes as to how to calculate this change in concentration here so we can calculate the rate. Then once we know the rate, we can compare that to these concentrations and figure out the order of the reaction is. Okay, so let's do that. Okay, so in our equation we have IO3 minus plus 3HSO3 minus. And that goes to our products. Okay, so we know that we're going to use 10 milliliters, 0.02 molar IO3 minus and 10 milliliters, 0.002 molar HSO3 minus. Okay, so the first thing we need to do is figure out the initial number of moles of each reactant. Once we know the moles of each reactant, we want to figure out the moles of each reactant that reacts. And then we want to figure out the moles left over. Now, if we were to plot this information on the graph, here's how it would look. Okay, so this is our initial concentration of IO3 minus. Earlier today, for a different reaction, we said that the graph should look like this. That's how our graph is going to look. Okay, so here's what's happening. Here, you add the two solutions together at time equals 0. Then at some time here, the solution turns blue. So let's call this T equals blue. Okay, so in this, from this point here, from t equals 0 to this point, the solution is colorless, then all of a sudden turns blue. Okay, so this time is going to be delta t, which is the delta t in this equation here. Okay? So this is our delta t in our graph. That's going to be right here. Now, to figure out delta, okay, so this is going to be the concentration of L3 minus when it turns blue. Okay, what we want to do is figure out this change in concentration. And when we figure this out, this goes in the numerator of this equation. So once we know this numerator, we know what delta t is, we can figure out what the rate is. Okay? So we'll figure out how to do this calculation in class so we can figure out this change in IO3 minus concentration so we can do the calculation for today's experiment. Okay, so I'll see the 11 o'clock lab section in about 15 minutes, and I'll see the 2 o'clock lab section in a few hours.